All right, let's look at um, continuing these addition reactions involving alkenes. So we looked at Markovnikov's rule, uh, addition of an alkene to HX, and now we're going to look at Markovnikov's rule again involving a methyl shift. So Markovnikov's rule with a methyl shift. So what this means is during an intermediate, we're going to have an entire methyl group from a neighboring carbon shift over to the positively charged carbocation. So if we look at this molecule, let's say we have and we're going to add HBr to it. Okay, so this lone pair of electrons is going to add that electrophile, and remember that we have three lone pair like that, and this bond here is going to come to Br and give it an additional pair of electrons, making it Br minus. So what we have, we're going to lose the double bond. Now color coding this to make sure you're following along. This is a carbon with two hydrogens, okay? Now these two hydrogens were already there. Now with the addition of the electrophile, we have a new hydrogen on the carbon. Now remember that Markovnikov's rule says that the hydrogen is going to add to the carbon with the most hydrogen in the double bond. So if I compare these two carbons, the green and the red, in that double bond, the red carbon has the most hydrogens. So that's where the hydrogen electrophile H plus is going to add. Now, when I take away this double bond, a hydrogen adds to this carbon here, but my valence is deficient here. So my formal charge is going to be a plus on that carbon. Now let's examine this. We have a secondary carbocation. Okay. Now, if my nucleophile, which now I have Br minus, I have that instantly when this electrophile leaves. If my nucleophile goes here, that would give me this structure. And I'm going to write it for simplicity. I'm not going to write out all those CH3s. What I would have is this, that hydrogen that was there, and a Br. Okay? Now, the methyl shift, I'm going to write out this same reaction again. Okay? So what happens is this lone pair of electrons goes there, and not that lone pair, but the pi bond electrons goes there, and this sigma bond goes here. So Markovnikov rule is still in place. I'm going to have, these are the two hydrogens I had before, and this is the new hydrogen there, and the same plus charge. I have a secondary carbocation. But now, one of these methyl groups, if I move that entire CH3 group, including the lone pair with it, what that's going to give me is, still have my CH3 here. That's the same thing as that. And now I'm going to have that methyl group here, and I'm left with one methyl group there. Okay? Now, keep in mind that before your implied hydrogen, I had a hydrogen here, and that's the same hydrogen that was there. So now I have a plus charge here because I've moved an atom group with the bond consisting of those two electrons. And what I have now is a tertiary carbocation. Okay, and now my Br minus can come here, and it can give me this Br and that. So if I label these reactions, just say this is number 1 and this is number 2. Okay, since this tertiary carbocation was formed from the methyl shift, and here there was no methyl shift that gave us a secondary carbocation, this product is going to be more favored. Remember the second part of Markovnikov's rule stating that the electrophile, well, part 1 saying the electrophile is going to add to the carbon in the alkene with the most hydrogen, and the second part of Markovnikov's rule stating that your most stable intermediate is going to be formed. So this is your most stable intermediate. Okay, so if we were to name this, this would be 1, 2, 3, 4, 5. So what I have, 3 bromo, 2, 3 dimethyl pentane. All right, that's your most favorite product. And above here, I have 2 bromo, 3, 3 dimethyl pentane. See, that's 1, 2, 3, 4, 5. Yep. Okay. Now, I did have some correspondences from students. I said they could not quite follow the mechanism. And you have to keep in mind the implied hydrogen. Okay, so what I'm going to do is I'm going to write out this same reaction using the expanded Lewis structure. Okay, so if I write out the expanded Lewis structure, let's draw the skeletal first. Da, da, da. So there are 1, 2, 3, 4, 5 carbons. So I need to make a line of 5 carbons. 1, 2, 3, 4, 5. Okay. Between 4 and 5, need to put a double bond. So this is going to be a CH. This is going to be a CH2. Okay, on number 3, I have 2 CH3s. This is a CH2. And number 1 is going to be a CH3. Now, that's not the correct way to number for naming, but that gives us a established pattern. Okay, so now if I add HBr, we're going to do the most favored product first. So the addition of the electrophile H plus. So we know that H plus is going to add to that carbon. Okay, so I'm going to rewrite all of this again in red. So 3 carbons, 5 carbons. 1, 2, 3, 4, 5. And this is H, H, H. This is H, H. This is CH3. This is CH3. Okay, you still have your H there. We lost a double bond. We had the 2 H's before. And this new H is what added, which made that a CH3. And then we have plus a Br minus. Okay, now we've lost one bond on one of those carbons right here, so this gives us a formal plus charge, +1. Okay, now like I said, I'm going to go ahead and do the major product. So I'm going to methyl shift it, move this whole CH3 group and this bond containing the 2 electrons over here. Okay, so when we shift that out, we're going to have five carbons again. Okay, hydrogen, 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 CH3, hydrogen. Now this CH3 is on this carbon, and we still have the 3 hydrogens here. Okay, notice again, I've lost my octet. I have a valence of 4. Suppose I have a valence of 4, but I only have 3 electrons, so 4 minus 3, that gives us a plus charge. Okay, so then that Br minus can come here. And our final product, again, is going to be 5 carbons. And this is H, 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 H. This is going to be CH3, Br, H, CH3, H, H, and H. Okay? So if I number this for naming purposes, 1, 2, 3, 4, 5. Okay. So again, that's 3, bromo dash 2, comma 3, dimethyl pentane. Okay. So this structure is the same as, let's draw you 5 carbons, 2, 3, 4, 5, and on have that, and that, and that. Okay, so that's a kind of long explanation for the methyl shift. You need to be able to do the methyl shift. Okay, so your HX additions, all of that is one type of addition reaction. Let's move on to the second type of addition reaction. Say alkene addition reaction of water. Okay. And when I say water, I mean an acid catalyst. All right. So let's look at this for example. Let's look at this alkene, and we're going to add it to H plus and water. Okay. Now, let me put in parentheses, we're going to start with an alkene. And we're going to wind up with an alcohol. So this is one of your addition reactions that you can actually get an alcohol. Okay. This is going to be a Markovnikov's addition of H plus. So this is a symmetric alkene. Both carbons have the same number of hydrogens. So that's carbon, carbon, hydrogen, hydrogen, hydrogen. But if I did not have a symmetric alkene, if one carbon in a double bond had more hydrogens than the other, I would add that H plus to that one. So what your product is going to be is this. So your H plus, One H is going to go there, and on the other side, you're going to have an alcohol. Okay? Or you're going to add OH to the other side. So what this gives you is your product is the same as you have two carbons and an OH. So this is called ethanol. All right. Let's try another one that does not have a symmetric number of hydrogens. And let's put the double bond there. We're going to say H plus over H2O. All right. Now, draw out the same number of carbons. And I'm going to make this H red. Okay, so I want to add that H to the carbon in this double bond that has the most hydrogen. That has one hydrogen. This has two. So my two hydrogens here. The electrophile here. And on the other side, I'm going to add OH. Notice how all of your action in these addition reactions are taking place across the double bond. Everything is taking place across the double bond. Okay, so this structure is the same as 1, 2, 3, 4, 5. 2, 3, 4, 5. OH. So this is 2 pentanol or pentan 2OL. All right. So make one more note about this reaction. Your highest, and this is not the correct terminology, but students understand this better, your highest degree alcohol is formed. So what I mean by that is you form a secondary alcohol, okay, as a product. If I were to add this reversely and I were to put the H plus there and the OH there, okay, just for instance, like, oh, well, why does that go there and it go there? But if I were to add that in that sequence, this would give me a primary alcohol. So you want your most substituted alcohol. A secondary alcohol is most substituted, and I say the highest degree. So this product is not formed, and that's going to be true. This is true for all Markovnikov additions that produce an alcohol. So a secondary alcohol is more substituted than a primary alcohol. So your secondary alcohol is going to be your product. Okay? All right, let's talk about another reaction. Let's talk about, this is the third reaction. Um, and the best way to call this is another hydration reaction. This is also a hydration reaction. Because we're adding H plus and OH. Okay, so we can have hydration again via what we call oxymercuration. Demercurization. And I'm going to abbreviate that OX D. All right. Now, this above reaction, reaction number 2, that is quite difficult to accomplish. It's feasible, but it gives a very low yield. And easier, which may seem a little bit more complicated, but an easier way to synthesize an alcohol, accomplish a hydration reaction, is oxymercuration demercurization. So all I want you to do is to be able to recognize the reagent and how to go about getting the products. So what happens with this, we have what we call HgOAc in water and sodium borohydride. Okay, so this is mercuric acetate. That's the abbreviation for it. And what your product is going to be, let's write out our implied hydrogens. That's carbon, carbon. All right. Now, this is a Markovnikov addition. This is a Markovnikov addition in that your H plus is going to add to the carbon with the most hydrogen. So H plus is still your electrophile. It's going to be a case where our electrophile is going to be something else in a minute, but H plus is our electrophile. So if I write this out, okay. So we're going to have a H added to the carbon with the most hydrogen, and on the other side we're going to have a OH. So all of this stuff, that's all you need to remember. Okay. And again, this is going to produce your most substituted alcohol. This is again, secondary alcohol. Okay. So if I added, if I added H here and OH here, this would be incorrect. This gives us a primary alcohol. Okay, and that would be incorrect. All right, that's the third reaction. Let's talk about the fourth reaction. And the fourth reaction is similar to this one, very similar, except what acts as a nucleophile. We had water acting as a nucleophile, or OH minus acting as a nucleophile. This is called the alkoxy. Alkoxy mercurization, demercurization. And the key to this is we have an oxy. So we have an alkyl with a oxygen. And this is really going to be an alcohol acting in this case. So I'll call this the ALOXDE. Okay. Now, I try to give you different alkenes. That way you can see what's going on. So let's start with methylcyclohexene. Okay. So again, we're going to have HgOAC. And this time, instead of water, we're going to have an alcohol. So your alcohol, ROH, is just like adding. This is not the correct term, but to keep you from getting confused, it's just like adding RO. Okay? So that H during the mechanism is lost, abstracted. Okay? So let me just make a alcohol CH3, CH2, CH2OH. Okay? And it's going to be reacted all again with the reducing agent NaBH4. Okay? So draw the same thing you have without the double bond. All right, now, which carbon in the double bond has the most hydrogen? That would be this one. So this is where the H would go. Okay. And on your opposite side, we're going to you just have to remember to remove that hydrogen and bond that to O. It's going to be CH2, CH2, CH3. Okay. Now, like I said, during the mechanism, this is actually one of the last steps. This is abstracted, but you just need to remember that this O is bonded to the other carbon where the double bond was. So in this case, we start with an alkene functional group, and you have to recognize that this is ROR, functional group, which is an ester, an ether, ETHER. Okay. All right. Let's talk about another alkene reaction. One of my favorite reactions. For the scope of where things are now, we're not going to do this mechanism. This is a very good mechanism. We're just going to focus on the product. So this is the hydroboration oxidation. All right, the hydroboration oxidation reaction. These are all reactions. And this is anti-Markovnikov. That is anti-Markovnikov. So when we have something that's anti-Markovnikov, make a little side note. When something is anti-Markovnikov, you can think about H going to the carbon in the alkene with the least amount of hydrogen. Anti-Markovnikov. That's H plus going to the carbon with the least hydrogen. Now, that's not how the mechanism works, but that's what you need to know. Okay, that is what you need to know. Your H plus is going to go to the carbon with the least hydrogen when it's anti-Markovnikov. All right, so let's take this same example here. The same example. Now, hydroboration oxidation, you need to be familiar with the reagents. We have BH3, tetrahydrofuran, H2O2, and some people write OH minus or NaOH. All right, so I'm going to write out in blue that hydrogen. So we have this methyl group here and we have that hydrogen. So what's going to happen is your hydrogen is going to add to the carbon with the least amount of hydrogen. This carbon right here has no hydrogen. So I'm going to add a hydrogen there. And on the other carbon, you're going to have an OH. Okay? So this forms the smallest, and this is not the correct term, the smallest degree alcohol Okay, so another way of saying that, the least substituted alcohol. See, this product is a secondary alcohol. If OH were to add here, and you would have a tertiary alcohol, and that product would be wrong. Okay, so your, let's just say least, your hydroboration oxidation is going to form the least substituted alcohol. Okay. All right. Let's see. On to reaction number 6. And this is going to be the addition of a halogen, X2. So Br2, Cl2, of that nature. Okay. Now, what I do want you to know is the product. I want you to know the stereochemistry for this product. No, stereochemistry, and that's dash wedge. Okay. So if we had cyclohexene and Br2, okay, you would have one Br projected one way and the other Br projected another way. So that would be a trans product. Okay. Now, let's do another reaction. And Br2. Okay. So I need to draw out the same amount of carbons, leave off the double bond, and we're going to have a trans product again. Excuse me, not a trans product, but a projection in the opposite direction. Or I can project this toward me and this one away. So project this one away, and this one towards me. So these two are actually enantiomers. And look at what we have here. We have chiral centers. So I'm going to let you draw the Fisher projections. And name using absolute configuration. So this is one of your assigned problems along with the one that I'm going to do, the problems I'm going to give you at the end. Okay, now this is the addition of X2 halogen. Let's keep rolling along. Let's keep rolling along. And addition reaction number 7, we're going to have what we call a halohydrin. And that's a halogen and water. Okay, so what you actually have is you're going to have some X2 over H2O. That's going to be your reagents. And this is going to be Makarnikov's addition again. We're going to say MKV addition, where BR acts as the electrophile. Okay, so prior to this we had what, H plus acting as the electrophile. This time we're going to have Br. So I'm going to start with another alkene, and we're going to say Br2 over H2O. You know, I could draw the plus here, or I can just draw the arrow. It doesn't matter. Sometimes I do both of them. Okay, so this does have stereochemistry. For this reaction, we need to show stereochemistry. So we need to know which way the atoms are projected, okay? So without stereochemistry, so if I add Br to the carbon with the most hydrogen, and the other side I'm going to add an OH. So as you can see here, this carbon had the most hydrogen, so I added Br to that. So we had that. And OH goes on the other side. Okay? So the stereochemistry of this is they actually, your OH and your Br, they actually project in opposite directions. So I could have OH coming to me and Br going away like that. Okay. Now I have 2 hydrogen here, and the stereochemistry isn't of any significance. Now if I do another example, let me see, can I make up? Let's say this, double bond there, and an ethyl group there. And I'm going to have Br2 over H2O. Okay, so I want to draw all of this out again without the double bond. Okay, so Br is going to add to the carbon with the most hydrogen. This has one hydrogen. Okay, so I have the one hydrogen here, and your Br is going to go here. Okay, and my OH is going to go there. All right, now this is without stereochemistry. This is without stereochemistry, this one above. All right, now let's put some stereochemistry on it. Let's see which way was projected. So I want to draw out again everything. Okay, so I can have Br projected towards me, and I can have OH projected away. And this would be, I just write out CH2, CH3. Okay, or I could have Br projected away from me. I could have OH projected towards me. And CH2CH3 going away. Okay. Now we can draw the Fisher projection. So this is the second one that I want you to do. Okay, I'll give you the first one. Let's see. And Br, H. So it's on the wedge right here. It's going to be OH. And this is going to be CH2CH3. Okay. So if we're looking that way, let's see, what are we going to have? We're going to have this CH3 going down, and over to my left is going to be what? CH2, CH3. Over to my right is going to be a OH. Br is behind OH. H is behind CH2, CH3. And going down is CH2, CH3. Okay. Now, assign R and S and name. Okay. Now, I also want you to draw the Fisher projection for this one, and name it using the absolute configuration. Okay, so throughout this video I'll be assigning problems, so you have to pay attention as to what exactly I am saying. All right, let's look at reaction number 8. Just having a good time with these addition reactions. We have another reaction. So the difficulty with this chapter is just really perfecting your reactions and remembering the stereochemistry for the ones I ask you to. All right, we have what we call catalytic hydrogenation. Okay, so actually that's going to be H2 over some catalyst. Platinum, palladium. Okay, so these are your catalysts. You don't have to worry about those. So, let's give you a reaction like this. And if we have H2 over that catalyst, this is one of the most simple reactions. You're just reducing the alkene to an alkane. So you're just really adding hydrogens on both sides of these because you already had these blue ones. Okay. So you're adding hydrogens on both sides of the double bond. Now, there is stereochemistry with this in that both of the hydrogens are going to project in the same direction. So if I put a wedge on that one that was added, they're going to project in the same direction. Okay. Now, number 9, we have epoxidation of an alkene. Okay. Epoxidation of an alkene. So what do you think is going to happen? We're going to start with an alkene. And we're going to make a epoxide. Okay. Now we're going to use the reagent peroxy acid. So a peroxy acid has the functional group RC double bond O, bonded to O and H. This extra oxygen makes it a per. So any type of peroxy acid, let's say we have this, and I'm going to write just peroxy acid. Okay, so what happens is you're going to make an epoxide. So we're going to drop the double bond again. Now, where the double bond was on both carbons, I need to draw a sigma bond, and put an oxygen in the middle. This is your epoxide. Okay? Now, one of the most common peroxy acids is something called MCPBA. All right. And what that stands for is meta chloroperbenzoic acid. Okay. Now, on the exam, you don't know what meta is yet until the second part of this course. But on the exam, you will need to know the structure. This is MCPBA. So when you see MCPBA as a reagent, it's going to act as a peroxy acid. Okay. So if I do this reaction, let's start with something simple like cyclohexene and all right, MCPBA. Okay. So you need to draw everything but the double bond. I need to make a line from one end of the double bond, other end of the double bond, and oxygen in the middle. Now, of course, this projects up or down, but we don't need to know exactly the dashes and wedges. Okay, so this is your alkene. This is your epoxide. Now, along with this reaction, we can take the epoxide and make a diol, or the same thing. A diol is another name, is glycol, G-L-Y. Okay, so let's take the epoxide that we made. Let's take that epoxide we made and let's treat this with an acid. Now you can see H3O plus. Sometimes you'll see H plus over H2O. Either or is sufficient. Now, what you're going to do when you react that with an epoxide is I'm going to make one side where the epoxide is. One side's going to be OH in that triangle, and the other side is going to be an OH. Okay? Another example. How we formed the epoxide before. H3O plus. OH and OH. All right, we don't have to worry about the stereochemistry of those. Now, that was number 9. Number 10. We have ozonalysis of an alkene. Okay, so ozonalysis of an alkene. That's going to be ozone at low temperature, minus 78 degrees Celsius, over dimethyl sulfide, which is CH3 2S. Okay, so this reaction is real easy. So I'm going to draw out your implied hydrogens. One here and one there. Okay, now what we want to do is, this is one of the reactions where an alkene retains a double bond. It's going to be a double bond O, but it retains a double bond. So I want to split this in half, okay? So if I react that with O3, minus 78 degrees Celsius, what I'm going to get, I'm going to have two different products. I'm going to have this. So when I split that down the middle, I need to put a O on top of it, okay? And I need to come to the other side, make that double bond, and I need to put a O right there, okay? So this is that H and that's that H. So what type of functional group is this? This is, so we have these two products. So these are aldehydes. Okay. Now, there are cases where, depending on the substitution, if you have something that's tri-substituted, you're going to get a ketone and an aldehyde. If you have something that's tetra-substituted, your product's going to be two ketones. Let's look at an example like this. Okay. And again, O3, low temperature. So just imagine breaking that bond down the middle. And I want to draw everything. I want to halve that double bond. On this side, I would have this. And on the other side, I would have that. Okay? So this is what ketones. Do one more example of that. Okay, so again, just going to scissor that down the middle. So let me just show you, this is A, B, C, D, E, if we did that. Okay, so this will give us our product. Um, this, O, plus this, O. And let's look at what A, B, C, and D is. This is A, B, and this is D, C, and E. Okay, let me do that on the above example. This is A, B, C, D, E, F, like that. So this would be A, B, and F. I'm arbitrarily giving them letters so you can see where the carbons are. And this is C, D, and E. If I do the above example, with numbers. This is 1, 2, 3, 4, 5. So this would be carbon 1 and 2. And this would be 3, 4, and 5. Okay. All right. Now, I want you to take these two alkenes So take these two alkenes and I want you to take it through all the reactions. So 1 is going to be your HBr that we did at first. 2, H plus and H2O. 3, oxymercuration demercurization. Alkoxy mercuration demercurization. And I'm going to give you the alcohol here. Hydroboration oxidation, BH3, THF, hydrogen peroxide, okay, we're going to do the halogenation, Br2, with stereochemistry. Name, with the stereochemistry, the name, and Fisher projection. Okay, your halohydrin, I'm going to do Br2, H2O. I want you to do the same thing that you did here. Let's see. Your hydration. Okay, then I'm going to let you take this, give you a new molecule, and I want you to take that epoxide and H3O plus, give me that product. And then number 10, I want you to take O3, O's analysis, minus 78 degrees Celsius, CH3 2S. So above here, this is going to be your first alkane. Take that through 1, 2, 3, 4, 5, 6, 7, 8, and 10. And your second alkane. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, and 10. I gave you an epoxide to make a compound with a number 9. And the second alkene that I want you to take all those through that's going to be the second alkene. All right, so take all of that through 1, 2, 3, 4, 5, 6, 7, 8, and number 10. All right. Now, in addition to this, I want to know which reaction. First of all, I want to know what is a vicinal dihalide and which reaction produces it. Okay. Fourth question. What relationship is a glycol to the word what relationship is a glycol from epoxidation to the word vicinal. Okay, so everything that I've asked during the video and these problems is worth 10 points. It's worth 10 points. It's good practice for chapter 8 of the exam. Okay. So next time we will pick up with alkynes, which is chapter 9. This does finish up chapter 8. So our next lesson plan will be on chapter 9.